Have you ever just stopped and looked at something, like a boat on the water, and wondered, how does that really work? It seems so simple, right? But when you start to dig in, you find these fascinating little puzzles hidden in plain sight.
Okay, so let's get right to the heart of it with this classic question. You toss a tiny little pebble into a lake, and poof, it sinks straight to the bottom. No surprise there. But then you have a colossal ship, we're talking thousands of tons of steel, that just cruises along on the surface. How in the world is that possible? Well, that's the big mystery we are going to solve together today.
So, here's our game plan. First, we're going to get a solid grip on what density is all about. Then, we'll introduce the force of buoyancy. After that, we'll dive into Archimedes' famous principle and use that to figure out how ships actually float. And finally, we'll look at a really handy shortcut called relative density.
All right, let's start at the very beginning. The absolute foundation for understanding why things float is density. Everything really hinges on this one concept.
So what even is density? Well, put simply, it's about how much stuff, mass, is crammed into a certain amount of space, or volume. Think of it as how tightly packed everything is. A block of lead is way more packed with stuff than a block of wood of the exact same size.
And you guessed it, there's a formula for this. It's actually super simple. Density equals the mass of an object divided by its volume. That little equation, it's the key to pretty much everything we're going to talk about.
Now, in physics, we have to be precise, and that means using the right units. So, D for density is measured in kilograms per cubic meter. M for mass is in kilograms, and V for volume is in cubic meters. These are the official international standard units, so we're all speaking the same scientific language.
Okay, let's look at some actual numbers to make this feel more real. Water, and this is our big reference point, has a density of 1,000 kilograms per cubic meter. Now look at mercury. It's at 13,600. You can immediately see just how much more packed and dense it is compared to water. That's a huge difference.
So we've got density, which is tied to an object's weight pulling it down. But that's only half the story. There's another force in the mix, a force that pushes up from below. And we call this buoyancy.
You've totally felt this before. Anytime an object is in a liquid, that liquid pushes back up on it. That upward push is the buoyant force, sometimes called upthrust. It's the very reason you feel lighter when you're in a swimming pool.
And this brings us to this incredible battle of forces. It's really that simple. If the object's weight pulling down is stronger than the buoyant force pushing up, it sinks. If the two forces are perfectly balanced, it floats. And get this, if the buoyant force is actually stronger than the weight, the object will rise up until it floats.
Now, this whole idea of a battle between weight and buoyancy wasn't just some random guess. It was figured out with amazing precision by a brilliant guy more than 2,000 years ago. And that brings us to the one and only Archimedes Principle.
There it is, straight from the source. Archimedes realized that the upward buoyant force on an object is exactly equal to the weight of the liquid that the object shoves out of the way. This idea of displaced liquid is the huge aha moment.
So what exactly is this displaced liquid? It's way simpler than it sounds. Imagine getting into a bathtub that's filled to the brim. What happens? Water spills over the side, right? That's displaced water. The volume of that spilled water is equal to the volume of your body that went underwater. And here's the magic part. The weight of that spilled water is the exact amount of buoyant force pushing up on you. And trust me, this is not just some dusty old idea from a textbook. We use Archimedes' principle all the time. It's absolutely fundamental for designing ships and submarines.
It's how special tools called hydrometers can tell you the density of a liquid. It's even used to check the purity of milk.
Okay, we've got all the pieces of the puzzle. We know about density, we know about the upward push of buoyancy, and we know Archimedes' principle. Now, let's connect all the dots and finally solve that paradox of the giant steel ship.
So this is the golden rule, the core of it all, called the principle of flotation. For something to float, it has to push aside an amount of liquid that weighs the exact same as the object itself. The forces have to be perfectly in balance.
And here it is, the big reveal. A pebble is just a solid little rock. It sinks because it can't displace much water. But a ship is cleverly designed to be mostly empty space. That huge, hollow hull acts like a giant scoop, pushing a massive volume of water out of the way. The weight of all that displaced water is enormous, which creates an equally enormous buoyant force. And that force is strong enough to hold up the entire weight of the ship. See? It's not about the steel, it's all about the shape.
All right, now that we get the deep physics behind it, let's talk about a super practical tool that makes things a bit easier, especially when we're talking about floating in water. It's called relative density. Relative density is really just a simple comparison. It's a single number that answers the question, how dense is this thing compared to water?
And the formula for it is just as simple as the idea itself. You just take the density of whatever substance you're curious about, like say iron, and you divide it by the density of water. What you get is a direct comparison, a simple ratio.
And we can even think about this in a slightly different way. Since density is just mass divided by volume, this second formula works too. If you take the exact same volume of your substance and water, the relative density is just the ratio of their masses. It's another way of asking, how much heavier is my stuff than the same amount of water?
Now, this is a really important detail you gotta remember, because you're dividing a density by another density or a mass by another mass, the units completely cancel out. So relative density doesn't have any units at all. It's just a number, a pure ratio.
And this is what makes it so useful. It gives us this fantastic, easy rule of thumb for anything in water. If the relative density is bigger than 1, the thing is denser than water and it's going to sink. If the relative density is less than 1, it's less dense than water and it's going to float. It's that easy.
So, we did it. We solved the puzzle of the floating steel ship, all using the amazing physics of density, buoyancy, and displacement. It's not magic, it's just really elegant science. But here's a question to leave you with. Now that you have these tools, what other everyday mysteries can you solve? Why does an ice cube float in your drink? How does a hot air balloon lift off the ground? The principles are exactly the same. Go figure it out.